Deanna Echols in extending bridge life through crack mitigation. Deanna Echols is the Senior Business Development Manager for Commercial Programs and Infrastructure with Fatigue Technology.
So I'm here today to talk about residual compressive stress as a crack arrest method. If you listen to my bio, then you know that I am not an engineer. I do have a fine arts degree, but I have a lot of hard knock experience. So if you ask me really tough questions, I'll do my best to answer, but I may deflect and answer later. Cover very, very briefly, I want to save time, a little bit about FTI, but I really want to talk about cold expansion itself. A lot of people, as I've learned through talking to folks over the last day and a half, don't really understand what cold expansion is. So I want to give you a little bit of a primer on that. Our background, which is really aviation, and great thanks to Boeing for originally developing this process method. The development and testing that led us to success in bridge structures, current applications, and then some new stuff that we're doing that might surprise you, maritime and pulp and paper, and even the amusement park industry. So yeah, we are an aerospace company. Primarily, most of our business is in the aerospace world. We came into existence because of Boeing. Just a little bit about us, we're up in Seattle and we're owned by Berkshire Hathaway, so just in case you wanted to know. Cracks from cyclic loading can be mitigated and in some cases even prevented through compressive residual stress. So Boeing developed this back in the late 60s in response to actually explosive decompression of aircraft due to cracks starting in fastener holes. So those of you that are old enough to remember, there were some bad accidents on some Comet de Havillands back in the 50s. And this happened because cracks propagated from one fastener hole to another fastener hole, daisy chaining together, and eventually you would get an explosive decompression. More recently, in 1988, some of you may remember the Aloha Airlines incident where a 737 became a convertible in flight. That was also due to crack propagation between fastener holes. You know, holes are a stress riser, so they will cause cracks, and under cyclic loading, the cracks will continue to propagate. So Boeing developed a cold expansion process to mitigate this and by imparting residual stress into metallic structures. So it's been used as a crack repair in aviation, which may seem a little strange that you have a hole as a stress riser, but it can also be used as a crack mitigator. And that's because you drill that hole in front of the crack, you are given that crack tip a larger radius to distribute the stress intensity factor. So it does work for a little while. But as you're going to see here shortly, it's not a long-term fix. Cold expansion itself, the basic process, is about radial displacement of a material around a hole in order to generate that zone of compressive stress. So here's a quick video explaining how that works. You have to have a very precisely sized hole. For aviation, that hole has typically got a 3 thou tolerance. For our crack mitigation process, it's a 2 thou tolerance. So you've got that ream step to get that hole. I've had a lot of questions in the last day about perpendicularity. As long as you're able to get 2 degrees vertical to the hole, you'll be fine. Quality is important, so we do ask that that hole be checked prior to the treatment. And then for fastener holes in aircraft, a split sleeve is loaded onto the mandrel after the mandrel is checked for wear, loaded onto a hydraulic puller. Nose cap is there to react the forces against the structure. Placed up or introduced to the structure, and hopefully I can stop this. Okay, so as that mandrel pulls through, and as the major diameter of the mandrel gets right there into the bore, it's radially expanding the material out. You're getting a plastic displacement. So I apologize to those on the right side of the room. I'm going to be using the pointer on your left. So this area has gone from an elastic change into a plastic zone of deformation. The material a little further out is also into an elastic change, but as the mandrel exits, it's going to collapse back. When it collapses back, it's going to collapse around that plastically deformed material. And what that does is give you that zone of residual compressive stress. So you watch that here, you see that collapse down. So this has been used in aviation for actually 50 years now. We just hit our 50th anniversary here this year. It's a very good way to protect holes from the impacts of cyclic fatigue. Engineered residual stress from cold expansion is used for far more than aviation. It was adapted as an enhanced aviation crack arrest hole repair back in the 70s and 80s. It was actually put forward by the Australians, the RAF, for use on their F-111s. Some of you may remember Len Reed, he was my predecessor with the company, the Australian bloke. He was very instrumental in getting that into the Australian Air Force. But the U.S. has picked it up as well. So some of our older aircraft actually have crack arrest holes protected using this. Then evolved in the early 2000s for use in structural steels. In structural steels, we're able to further improve that by the action of a bushing that props open that hole. So here's the crack arrest process. It's very, very similar to what you just saw for the cold expansion process. The most important thing is finding that crack tip, and I'm pretty sure that your bridge crews are already pretty good at that. So once you've found the crack tip, we put a very precisely shaped hole in front of it. We want to lead that crack by a 1/16 of an inch ligament. That is so that when we actually use the hydraulic forces to impart the residual stress, if there's any micro cracking, we want to grow it into the mitigation area. It also gives you a little bit of a fudge factor in case you miss the crack tip, that you get that crack into that zone of compressive stress. Checking the mandrel for wear, sliding that sleeve onto the back. It's not split, so it can't go on the front, obviously. Putting it up to our structure. And again, we are going to install this both plastically deforming the bushing and the parent structure and getting that zone of residual compressive stress. So that crack tip is actually caught in that zone of compressive stress, seriously reducing the stress intensity factor and retarding further growth. From CX to protect fastener holes all the way to what we're doing now is through a series of developmental testings. I don't want to spend a lot of time on these tests because they're for the basic CX. But we looked at the fatigue life improvement due to cold expansion. The bottom line is a hole treated with nothing. It's just an open hole. And then you have that blue line is a hole cold worked. The next two lines are the one second from the top is a metal with no hole. And then that top one is a hole that's been treated and then has a net fit fastener. So when you put that net fit fastener inside that hole, it makes it even stronger than if there was no hole at all. When you install an interference fit fastener into that hole, the protection gets even greater. Here's where it really starts to play into crack propagation for our structures, is in the time it takes for a crack to go from visible to critical. So if you look at these curves, here is a hole that is not treated, and here is one that is treated. So the crack growth, once it hits critical length, is about the same. So that vertical climb is the same. But what's telling here is the change on the x-axis. You get a much greater length of time before that crack starts to grow between initiation and critical length. So that's where you get that real improvement. As I said earlier, this was done in the introduced in the early 80s for crack repair for aviation, with an additional testing showed that if we put that interference fit pin into the hole, it would make it even better. And then in the 2000s, we started looking at this for structural steels for infrastructure. We found that that residual stress is compressive at the whole bore, reducing the mean stress during in-service cycling, which is obviously very helpful for crack arrest on your structures. So the way we do things at FTI is very methodical and deliberate. We always start with finite element analysis, then we go to lab testing, then we go to field testing before we ever put something out in the field. We've done this with our crack arrest, and I don't know that I've ever shown you guys the FEA before, so this hopefully is interesting to you. So what you're seeing in this first slide is simply the matrix for the FEA. So then we go ahead and show the installation of the bushing with the residual stress in a coupon under load and another coupon with no load. So you can see that you've got the residual compressive stress here, and then you've got tensile stress in the far field. So what we're doing is we're pushing that tensile stress away from the hole itself. Now if we put those coupons under load, you'll see that the hole that is not treated is just a hole with nothing in it. You've got the tensile forces all around the hole itself. And so that's what's going to be acting on that crack, right? So those tensile forces are right there. But with the treated hole, with the crack arrest and the bushing, the tensile forces, again, are pushed way out so that we have the 13.5 KSI here, 20.5 KSI there. So the FEA supported our assumption of what was going to happen. Okay, we then did lab testing. We had both lab testing internally, but we also had some external lab testing. Southern Utah Engineering, 6 coupons with a spare, and basically it was cutting a notch, putting in the MTS frame, running it until you got a crack, And then we were looking for two different events. We wanted to see when the crack reached the hole and then how many cycles it would take to reinitiate on the other side. So the results were pretty astounding. The crack arrest holes, the normal way that you do things now, all of them failed pretty rapidly. The best one went to 440,000 cycles, the worst one at 230,000 cycles. The ones treated with the crack arrest, with the bushing, with the stop crack process, all made it to 4 million cycles, and the test was cut off. The spare was run as well just to see how long it could go, and at 20 million cycles, the test was ended. Pretty positive. Now that is a test in a very simple condition. That's just tensile loading in two directions, a push and a pull. So understand if there's some skepticism about that, because your bridges just don't load in one direction. So get that. So we later did some field testing. We also looked at a welded test coupon because, as you know, most of your cracks come from some feature like a weld seam. So how could we protect or put in a crack arrest hole near a weld seam? And because that residual stress field actually gives you like a radius around that hole, all the way around it, you can actually put your treatment in adjacent to the weld line and still capture the crack tip in the compressive field, keeping it from growing. So in the tensile test that I just showed you, we got a 13-to-1 improvement. On a weld line, we managed to get a 3-to-1 improvement. So still pretty satisfactory considering the standard alternative. We've also recently done some corrosion testing because we are putting, steel in steel. So you are going to get some corrosion. So we wanted to do some testing to see what kind of problems that would do. So we used our standard 304 bushing. We also used a 17-4 bushing, which is our alternative bushing for stronger steels. And then we also put a 1018 bush in there. And the reason we did that is because we're doing work now in some structural steels for the pulp and paper industry, and they use a lot of 1018. So we wanted to see what would the corrosion look like with that. So we did a 1,000-hour salt spray, and what we found is that the base material didn't corrode more because of the presence of the bushing. It just corroded in an even manner with it. So you just treat it like you would any material. If you have to paint it, then you paint the bushing as well. So there's really no impact that we could see. We have FEA, and then we have lab testing, and then it was time to do some field trials. So we did 3 monitored field trials, 2011 and 2012, in 3 different environments to try to give us some good ideas of what it would look like. So we had the Manahawkin Bay Bridge in New Jersey that was done in a sort of a littoral environment. For heavy loads, we had the Lincoln Tunnel Interchange. That's also where the weld seam test was done. And then we had just kind of a normal traffic bridge in New York over the Delaware River. To date, those we have not had any report of crack propagation. So been pretty satisfied with those. So from that point, we said we're ready to go, and we're ready to put this out there. We did. So we figured we knew that we had this foundation from an aerospace application, good FEA support, lab testing, and then some good field results. Currently, many of you already use this, many of you don't. And those of you that don't, I'd love to chat with you and maybe understand what your concerns are, and we can talk further about that. Chris Keegan here in the audience, he and I did a survey last year to try to talk to some of you about why you use this or why you don't. We got kind of a limited response, but of those that did respond, the ones that said they use it said they like it. With one exception, folks were pretty positive, and nobody had any in-service issues to report. I would be interested if you are using it and you do have an in-service issue. I would love to talk to you and understand that, because as of right now, all the feedback I have has been very positive. So other miscellaneous uses, we've been used in an amusement park to protect structure there. I recently started putting it into port material handling equipment and a North Sea oil rig. We're going into some new applications that we've been developing for both maritime and lime kilns. The maritime is the same process that we use now for structural steel, but the lime kilns are a little more interesting. They require the hole to be filled because a lime kiln has material on the inside of it, and you don't want that to come out, even though we're not drilling through their insulation refractory. But so we came up with a plug. So we now do the same process, but we drive an interference pin through that to plug the hole. Several repairs on some lime kilns in the Pacific Northwest, and they've been monitored for close to 2 years now, and no problems. And these, if you're a kind of a loads geek, these are really interesting because these kilns, not only do they have the rotational cycling that give it that, as it goes to the top, you get that compressive load, loading, but they've also got thermal cycling because there's a lot of high temperature going through those kilns. So it's really actually a fascinating project. Then with our maritime application, we partnered with a classification society. We did another test in the lab, showed a 13-to-1 improvement using their steel materials, AH32, which is a little different from A36, which is what you guys normally have in your bridges. And then we did a field test on a ship going back and forth across the North Pacific. Really kind of interesting. This ship went back and forth from San Pedro, Long Beach area up the Pacific coast, even made a stop in Tacoma, and then crossed the North Pacific to go to Korea. And it did this, we monitored this for 3 years, going back and forth. A lot of storms in the North Pacific, a lot of interesting loadings going on in that ship, and they monitored they monitored the mitigation using acoustic sampling. And what they discovered after filtering out the wave noise, what they discovered was that there was no activity in the crack upon mitigation. So it was a pretty good result. A conclusion, using the enhanced crack arrest really reduces the stress intensity at the crack tip. I mean, we know that you're never going to repair a crack, right? You have to take it out and replace the structure. But you can mitigate it, and this is a really good way to mitigate it by putting it through this process and putting it into residual compressive stress. We've done a lot of work on this. As I've just really touched on, we've got a lot of engineering thought behind it, the FEA work, analysis, a lot of lab testing, a lot of field testing, and again, I've not had any negative feedback. So if you've heard of something negative, I'd like to know, but we think it's pretty good stuff. Well, I'll open it to your questions.
I was hoping you could talk just a little bit about the constructability. You were talking about how it's very important to be at a very prescribed distance from the end of the crack.
Yeah.
Could you compare that a little bit with drilling a large hole and the tolerances for where that would go? I guess it's not my
Sure. So I'm not an expert on the crack diameter or the crack arrest hole diameter for the traditional method, but I do know that you have to vary that diameter depending upon the length of the crack. So with the cold expansion process for crack arrest, all of our holes are 1/2 an inch. We make it very easy logistically. It's just going to be a 1/2 an inch hole. The only thing that's there are two things about that are important, though. I think that's what you're asking about. The first one is that hole does have to be a 1/2 inch, and it's got a 2 thou tolerance. The second thing, even though we will allow perpendicularity variance up to 2 degrees. The other thing is that we do want to lead that crack tip by a 1/16 of an inch. So you have to lead the crack by 5/16 so that once you drill that hole, you have that 1/16 of an inch ligament. And again, that is to allow you a little bit of fudge factor in case you miss the crack underneath, and B, when you're in tensile loading as you pull the mandrel through, you are going to get a little bit of micro cracking, and we want that micro cracking to occur in the direction of travel into the area. So if I didn't emphasize this before, that 1/16 of a ligament, or that leading it by 5/16, has to be done in the direction of travel of the crack. So finding your crack tip and understanding the direction of travel are critical.
You start talking 1/16 of an inch, and if it's a bridge crew that's doing it, I get nervous on exactly if they're going to find that tip and measure off exactly a 1/16 of an inch. Yeah, Chris?
Yeah, we've done it well over 100 times. Yeah, some mistakes have been made because, you're trying to do this work in an underbridge inspection truck. Everything's bouncing around, and so trying to hit that precisely is not easy. But our bridge crews have done it enough that they're getting pretty good at it. So, and in the hundreds or so, I think we've had 2 where it's popped out, and I think that's probably part of the reason is trying to do it in the wrong spot, or they put it in not exactly straight, and so there's a number of things that can happen, but in the hundreds or so, just having 2 that popped out, versus in the past, every time we have another inspection, we'd chase the hole and drill another hole, and I have pictures where it goes and goes and goes. So,
yeah, I appreciate that, Chris, and I'll add to that we started off only having 304 bushings because that works best in an A36 structure, but not all structures are made of A36, and some structures have a higher tensile strength to them, and in those cases we need to use a 15.5 or a 17.4 bushing. And I'm wondering, Chris, if maybe what happened on those structures as well is that the tensile strength of that steel was actually a little stronger than what that bushing could handle, and so they will the bushing will just fall out. The good news is, and as you've noted, we've had no propagation in those holes, even though the bushes fell out. That's because even though that bush fell out, the hole still had that cold expansion treatment done to it. So it still got that residual compressive stress. It's just not perfect because it's not propped.
Just a standard mag drill that you're using to drill?
We do recommend a mag drill because you do want to get that indexing every time between the pilot, the drill, and the hone.
Is there any difference between temperature application? Let's say if you put the bushing at 90 degrees versus 20 degrees?
No, that's a great question, though. Thank you. And it's something we spent a lot of time talking about for our kilns because they're so warm. So we want to make sure that our bushing and our structure have the same thermal properties so that they will grow and expand and then collapse at the same rate thermally. So no, there's no issue with that.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.